We continue in the hidden electrolytic village at a new site for the second test of the Chunin exams. Remember, we will always be given instructions to learn and then battle in the arenas for answers to various problems. For this second test, we have Anoki, the third Tsuchikage and current official leader of the village. He is going to help us understand the electrolysis of water and aqueous salt. Now, Anoki is a master of exceptional earth release technique. Despite his elderly appearance, he demonstrates remarkable speed and agility in battle. Anoki states, before we analyze the electrolysis products of aqueous salt solutions, let's examine the electrolysis of water itself. Now, very pure water is difficult to electrolyze because so few ions are present to conduct a current. However, if we add a small amount of a salt that cannot be electrolyzed, such as like Na2SO4, write that down for you, Na2SO4, this is a salt that cannot be electrolyzed, then the electrolysis process for water actually proceeds rapidly. So an electrolytic cell with separate compartments for H2 and O2 can be seen on the screen here. So we're going to have a compartment for H2 again, then we have a compartment for O2, and then we have our voltmeter that's going to be connected. For the electrolysis of water, the anode is going to have the half reaction of water, again losing 4 electrons to form oxygen gas. For the reduction half reaction at the cathode, we know we're going to have water that's going to gain 2 electrons and form H2 gas and 2 OH minus. And the overall cell reaction for this is going to be liquid water forming H2 gas and O2 gas. Exactly the little bubbles that you see bubbling up in our half cells here. We can also go further and verify oxidation and reduction by using oxidation and reduction numbers. So here for oxidation, we see a -2 value for oxygen, and then it goes to 0. So that means we had to have gained 2 electrons, and then to get down to 0, we had to lose electrons. Here we have a loss of 1 electron, and then we have 0. So we need to go from a loss of 1 electron up to 0. That means we need to gain an electron here. And also, because concentrations of H plus and OH minus are 1.0 times 10 to the negative 7 molar and not 1 molar, we actually are at non-standard conditions. So before, when we saw that some of our ions had everything in standard cell potential, and then we saw our water reactions have everything in non-standard potential, that is the reason why. The concentrations of our H plus and our OH minus are going to be 1.0 times 10 to the negative 7 molar, as we know from chapter 14 material. And since we are not at 1 molar, which we usually see for E naught of the cell, then of course we are not at standard cell potential. Anoki now wants to speak about aqueous salt solutions. He states, aqueous salt solutions are mixtures of ions and water. So we have to compare the electrode potentials of the ions and water to predict the electrode products. Okay, folks? So we want to know what's going to be where. We got to look at both the ions here and also the water, whatever solution we are getting. First, we must discuss predicting the electrodes in general, and then we will discuss over voltage, okay? So predicting electrode products is going to involve, again, comparing the electrode potentials or the potential half reactions for anything that's going to be reduced and anything that's going to be oxidized, or in other words, possible oxidizing agents and possible reducing agents. We find that when aqueous salt solutions are electrolyzed, the reduction is going to occur at the electrode with less negative or more positive potential, while oxidation is going to occur at the electrode with less positive or more negative potential. For example, in the electrolysis of a potassium iodide solution, so we have Ki aqueous, and so since we're in solution, we're going to have Ki mixed with water. Okay, and if we're dealing with the solution, that means we're going to have Ki ions mixed with water. To predict the electrode products, the first thing we want to do is gather our ions up. We want to figure out what could be the possible oxidizing agents and what could be the possible reducing agents. So to figure out the possible oxidizing agents, we know we're going to first think of our cations, right? So we're going to take our potassium here and of course water. Therefore, our reducing agents will be our iodine, anion here, and of course water. Let's compare the possible oxidizing agents. So we're going to have K plus, and then we're going to have water, and we're going to look at their cell potential. So we have the standard cell potential of negative 2.93 volts for potassium, and we have a cell potential of negative 0.24 volts for water. Water is more positive and therefore more easily reduced than K plus. That means that this is going to lead to the production of H2 gas at the cathode. And we can see the H2 gas production here at the cathode in the version of the electrolytic cell here. And I know some of you may notice, wait a minute, we have standard potential and then we have non-standard potential. Why is that happening? Well, we're going to talk about why one is standard and why one is non-standard next, okay? Well, now let's focus on our possible reducing agents. So we have our I minus versus, again, water. We have to look at the cell potentials from the half reactions, right? For oxidation, we are looking at the electrode with the less positive or more negative potential. So we have 0.82 volts and 0.53 volts. This one is going to be less. So our I minus is going to be at the electrode for oxidation, meaning it's going to be at the anode. You can also go further and say that iodide ion is less positive and therefore more easily oxidized than water, resulting in the formation of the I2 solid at the overall anode. Inoki then wants to dive into how additional voltage influences the actual products formed during electrolysis and helps explain why we have standard cell potentials and non-standard cell potentials being compared to one another. Inoki states, the products predicted from a comparison of electrode potentials are not always the actual products. For gases to be produced at metal electrodes, additional voltage is required. So overvoltage is going to be the additional voltage needed to produce gases at metal electrode. And that means in order for overvoltage to happen, it has to be greater than the standard cell potential. And so if it's greater than the standard cell potential, and therefore cannot be the standard cell potential, and so it has to be the non-standard cell potential, which is why if you do see something that has an addition of overvoltage, it will simply have the non-standard cell potential and not the degree symbol like we normally see with standard cell potential. Now, overvoltage needs to be taken into account when predicting the products of electrolysis for aqueous solutions. Why? Because we are dealing with water, and water is going to produce H2 gas or potentially O2 gas, depending if it's acting as at the cathode or the anode. So overvoltage for water is 0.4 volts to 0.6 volts. It is a range. Therefore, if I have water acting as in a redox reaction for reduction, acting at the cathode, and it has a non-standard cell potential of negative 0.42, my range, negative 0.82, because I will be adding 0.4, all the way up to negative 1.02, because I'm going to be adding 0.6 to my overall standard cell or non-standard cell potential. Okay, so that's what overvoltage does. It adds in this overall range. So when you see this value, you're really going to say, okay, I'm at negative 0.82 volts to a negative 1.02 volts. You can do the same thing here when water is going to be oxidized, and therefore be at the anode potentially. If you have a non-standard cell potential, of 0.82 volts, then of course you would add 0.4 to get your overall range there, and then that would be 1.22 volts to up to 1.42 volts, because when you add 0.6 to 0.82, you get the 1.42. And so that overvoltage is taken into account when you are producing gases. And so since water is producing those gases, we have to take the overvoltage into account. And that's why we see those non-standard cell potentials for some of our water half reactions. And of course, we always get the question, why is this important? Where overvoltage is actually a multi-billion-dollar process because it plays a pivotal role in determining the outcome at the electrodes, which therefore is going to impact the efficiency and economics of production of whatever we want to focus on. For us, in our example, we're going to focus on the industrial chlorine production. And how do we do that? We start with an aqueous solution of NaCl. So if we're dealing with NaCl, we have the ions of Na plus and Cl minus. Now, also, since we're an aqueous solution, we know we also have to focus on water. And we know water is going to form either H2 gas or O2 gas. So when we're thinking of NaCl ions and we have to compare them, we're thinking of what is going to be the oxidizing agents for reduction and what's going to be the reducing agents for oxidation. So let's go ahead and compare our metal cation to water, okay? So our cell potentials are negative 2.71 volts. And of course, for our water molecule, because it is going to potentially form H2 gas, we have to take into consideration overvoltage. And at the high end, it can have a negative 1.02 volt. So since the cell potential for water is going to be more positive, we have reduction at the cathode for water, and therefore H2 gas will be formed. Okay, now let's go ahead and look at the potential anode. We are going to be comparing our chlorine anion and water. So our chlorine anion has a cell potential of 1.36 volts, and our water molecule, when it's going to be in oxidation form, has a cell potential of upwards of 1.4 volts, or really 1.42 volts. So it looks like our chlorine value is going to be lower than our water amount. But we have to take into consideration that the water amount is an approximate value. So therefore 1.4 and 1.36 are very close to one another. So we need to add in another layer of information, and that could be something like concentration. For this overall example, the concentration of Cl- is kept very high. So if the concentration of this is very high, it's more likely to form the product of CO2 gas. If it's more likely to form the product of CO2 gas, then guess what? We're going to go with that standard cell potential over the lower concentration of O2 gas that's formed from water. Therefore, I would definitely be choosing our chlorine for our anode at oxidation. Now, will you have to get into all the nitty-gritty details like this for an example? Of course not. But of course, I want to give you all the details I possibly can for this portion of the example. Now, why is this important? Well, chlorine production is crucial for applications like water disinfection, chemical manufacturing, sanitation, and industries such as paper, pulp, and textile. This definitely means that it's going to impact public health and various manufacturing sectors. So that's why it's very important to understand, hey, if I can produce this, I can get the big bucks. Anoki now summarizes everything we know before battle. So in electrolytic experiments using aqueous solutions, cations of less active metals like gold, silver, or copper are reduced to the metal. Cations of more active metals, like our group 1 metals, for example, or our group 2 metals, are not reduced. So water is reduced to H2 and OH- instead. Anions that are oxidized because of overvoltage from O2 formation include the halides, except for fluorine. And of course, it's going to include the halides when the concentration of the halides must be very, very high. Now, anions that are not oxidized include fluorine and common oxoanions like sulfate, carbonates, nitrates, and phosphates, because the central nonmetal in these oxoanions is already in its highest oxidation state. So therefore, water is going to be oxidized to O2 and H instead. Anoki now wants us to take what we know to battle for test number 2. Welcome to our second battle to test our current understanding for Tsuchikage Anoki. We have Naruto versus Neji. Now, Naruto is part of Team 7, so our loyalty definitely lies with Naruto, folks. We'll be predicting the electrolysis products of aqueous salt solutions. So we want to use half reactions to show which product forms at each electrode during the electrolysis of aqueous solutions of the following salts. So we have lithium bromide, we have a silver 1 nitrate, and we have magnesium sulfate. So how do we approach this? Well, we definitely want to identify the reactant ions and compare the electrode potentials with those of water, because we are dealing with an aqueous salt solution. Of course, we definitely want to take into consideration of overvoltage for water and the formation of H2 and O2 gases. Now, most times, half reactions will be given to you, and I will be writing them as we go along, okay? But if you see them in a question, normally it will be given to you. For Macmillan, you have to basically click on a link, and it'll give you all the half reactions in another page, okay? Now, the reduction half reaction with less negative cell potential is going to occur at the cathode, while the oxidation half reaction with the less positive cell potential is going to occur at the anode. So that's just bringing about all this little information that we already kind of know. Also, since I know I am dealing with water, I want to have water acting as a reduction or being reduced acting at the cathode, and I also want to have water being oxidized acting at the anode, okay? To take into account overvoltage based on the values given with these two half reactions, I'll say for the reduction of water, overvoltage range is negative 0.82 volts to negative 1.02 volts. And so for the oxidation of water, overvoltage range is 1.22 volts to 1.42 volts. So we want to make sure that we are taking everything into consideration, and it just makes it easier for us to just grab and go and see, okay? Let's go ahead and start with letter A, or lithium bromide. All right, so the first thing we want to do is get our ions. So we have lithium bromide here. That means we're going to have Li plus and Br minus. We'll go ahead and get the half reactions for both of those. What we want to do is them by oxidizing agents and reducing agents. So oxidizing agents is going to be at the cathode and usually going to be dealing with cations. Reducing agents is going to be at the anode and of course usually dealing with our anions, okay? And of course, we are comparing them with what we're mixed with, and that is going to be water. So we're going to compare our lithium ion to water and our bromine anion to water as well. So let's start with our oxidizing agents to see which one of these are going to be produced at the electrode. That is the goal here. We're supposed to be using half reaction to figure out which product is formed at the cathode and the anode. So we're dealing with the cathode here first. So for lithium plus ions, to gain an electron to form lithium solid, the standard cell potential is negative 3.05 volts. And then we have for water, when it is gaining 2 electrons to form H2 gas, and of course 2OH minus aqueous, we have a standard cell potential of negative 0.42 volts. But of course, since we're dealing with water, we have to take into consideration over voltage. So the over voltage of water give us a non-standard cell potential of negative 0.82 volts to negative 1.02 volts. Okay, folks? And so we are comparing this value to this value here. And we need to figure out which one is the most positive. And the most positive value is going to be the smallest one here. And so as we can see, the smallest one is going to be for the half reaction for water. Therefore, water is going to gain 2 electrons at the actual cathode, and it's going to form H2 gas. So the product that forms at the cathode is going to be H2 gas. That will be the answer there. We'll do the same thing for the reducing agents. We have our bromine that has a standard cell potential of 1.07 volts, and then we have our water that has a standard cell potential of 0.82 volts. But with over voltage, we know it can go up to 1.42 volts. And so we're really looking at 1.42 volts versus 1.07 volts. And since this is at the anoic region, right, or the reducing agent, then we are looking at the smallest value. So the smallest value here is going to be 1.07 volts. And so that means that Br minus is going to form Br2 liquid and release 2 electrons. So I can say at the anode, Br2 liquid is definitely going to be formed. We're going to be completing this same process with letters B and C. So let's go ahead and get that set up. All right, so let's start with letter B. We have AgNO3 or silver 1 nitrate. So that's going to break down into Ag plus ions and NO3 minus ions. And of course, they're going to be mixed with water because this is a solution. So we're going to break down our oxidizing agents for our cathode and our reducing agents for our anode. Now, using previous knowledge from the summary Inoki gave us, we can say that cations of less active metals are reduced to the metal. So automatically we can look at the Ag plus and say it rather gain an electron to form Ag solid. So yes, there will definitely be our cathode here, or the product that's formed at the cathode over water. And of course, we're also looking at our cell potential values, and this one is more positive. So that makes sense as well. Now for the reducing agent, we are looking at our nitrate versus water. And NO3 minus cannot be oxidized further. It's at its highest oxidation state. So again, based on the summary Inoki gave us, we can say that it's going to be water that is going to end up being our reducing agent and therefore being oxidized and at the anode. So what's going to be the product, is going to be O2 gas here. And we can do the same thing with letter C, or magnesium sulfate. So we're going to have Mg2 plus and SO4 2 minus, and of course water. So for our oxidizing agents at the cathode, we're going to have magnesium 2 plus gaining 2 electrons to form magnesium solid with this potential standard, this standard cell potential, and then we're going to have water with its over voltage potential of negative 0.82 volts and negative 1.02 volts. Now Mg2 plus, based on the standard cell potential, is going to be a much weaker oxidizing agent than water. So we can say that H2 gas is going to form at this electrode for letter C. Now moving on to the reducing agent, we have SO4 2 minus. SO4 2 minus can't be oxidized further. It's at its highest oxidation state, using again the information we get from the summary from Inoki. So because of that, that means water is automatically going to be oxidized at the anode. And so we're going to be producing oxygen gas here. The second test is over, folks. Naruto was able to remember everything Gramps Inoki said and beat Neji for the win. Let's get to the third and final Chunin exam. See you there.